Have all of our committee members here, and it's wonderful to see so many friends and family and colleagues here for Javier's defense. This is a big day. I have the honor and privilege of introducing Javier and probably explaining to a good chunk of you what this poster that you're seeing here is all about. So in my group, we have a tradition of making posters to introduce PhD defenses in the theme of movies, and they get personalized to capture certain things that are especially relevant of the person defending. So for Javier, you might recognize this is an adaptation of the movie Borg v. McEnroe. So, Javier is a very accomplished tennis player, and I'll tell you more about that in just a second. And so we photoshopped Javier onto the body of young McEnroe, which I guess is actually quite appropriate, seeing as McEnroe himself was a Stanford tennis player back in the day. This elk that is taking the place of Borg in the background, that'll make sense by the end of Javier's defense, I promise. And what he's wielding instead of a tennis racket is a GPU, device for parallel computation, which has been the workhorse behind a lot of Javier's work that you'll hear about in his thesis, which is on bringing together ideas from dynamics and optimization to parallelize what seem to be on the surface inherently sequential problems. Now, before I hand it over to him, I want to tell you a little bit about Javier. So first of all, I'll tell you about his official CV. His CV is quite impressive. He received his undergraduate degree in mathematics from Harvard University, summa cum laude. He went on to be a Rhodes Scholar at Oxford, and since then has been a PhD student here at Stanford in statistics. His thesis is really centered on a couple of works, his own first author works on methods for parallelizing sequential processes, many of which appeared at NeurIPS, and then one most recently in TMLR. With exciting applications of these ideas that he's done in collaboration with others in the group, parallelizing fundamental computations for statistics like MCMC. And next, where is he off to? Well, he's going to be joining the technical staff at Unconventional AI, which is a startup that is doing all sorts of really exciting work at the interface of AI and neuroscience, actually taking neuroscience inspiration for how we can build new hardware that maybe is able to compute more efficiently. And in this picture that you see in the bottom right, Javier is actually sporting an Unconventional AI shirt, I think. I heart nonlinear dynamics. It's quite appropriate. So now that you've heard all the official stuff, let me tell you the stuff that you may not have known, the unofficial CV. So first of all, Javier is a champion tennis player. He was on the varsity team at Harvard when he was an undergraduate there, continued to play at Oxford. And really this skill generalizes beyond just tennis to pretty much any racket sport. So here you can see him dominating many others, though I guess Andy may take offense at that, in the group at various squash, pickleball, you name it. Javier is quite the competitor. He's also a very accomplished dancer. He's been a member of the Stanford Viennese Ball, and so I gather that's coming up this weekend as well. So, big event. He is a native of San Diego and Houston, and what you see in the top here is actually a lovely picture of us having a party that his mom very, very generously hosted for us at NeurIPS this past year down in San Diego, which was a ton of fun. Now, one thing I want to also point out is that Javier is not shy about telling us what he thinks about the Stanford winters. The weather here is great, except for the winters are brutal. I feel like that may be the overstatement of the year, but it's consistent. The winters you'll see him quite bundled up here. To his credit, Javier was an early adopter of AI. So these messages, the dates are a little bit small, but these are January of 2023, shortly after ChatGPT was released, and Javier was quite gung-ho about adopting it. And some of these messages are actually kind of fun to look at now in retrospect. So this first one is, what do you think about this thread? Apparently this guy used ChatGPT as a coding assistant. He asks it to do various tasks, and it takes a stab, and then he tweaks it. Nowadays it's crazy to think, but could you imagine a world where you didn't do that? Javier is incredibly ambitious. This has been true since day one when he approached me about doing a rotation in the group. His interests span everything from statistics to computing to neuroscience. And I think that what's true across all the projects is that you've always had an eye for, like, what is the biggest impact that I can have? How can I go out and really make a change in the world with my work? I think you're an incredibly creative scientist, and I think that's going to become very clear as we see the thesis presentation today, bringing together ideas from all sorts of different disciplines. You're an earnest person. When you set your sights on something, you hit it with conviction and intensity. And I think that as much as creativity and great ideas are important in this field, really it also just takes a lot of hard work and a lot of dedication, and that's certainly true of you. And finally, I really appreciate the generosity with which you've shared your expertise and your insights and your time with so many of us in the group over the years. So, Javier, it's been a real pleasure, and I'm excited for your thesis defense.
Well, yes, thank you so much, Scott, for the really generous introduction. And today we're going to talk about unifying optimization of dynamics to parallelize inherently sequential processes. This is a bit of a mouthful, so let's start to digest it. There's going to be three main ingredients in today's talk. One of them will be optimization. This is the broad field of taking some sort of goal and minimizing it. There's a function, you want to make it small or make it large. This will also encompass dynamics, which we experience in our daily life. It's how things change over time. And you can think of it as the study of how a system might change over time. This is an animation showing a dot traversing through space, moving through it dynamically. And then finally, this talk will include, as Scott referenced, parallel computing, which in a nutshell is the idea of taking many workers all at the same time and divvying up a task to accomplish it more quickly. So we will touch on all three of these elements throughout the talk: optimization, dynamics, and parallel computing. We'll necessarily need to provide some background on all of these. Let's start with background on parallel computing. So what is parallel computing? The basic idea is that some tasks can be divided between workers, so those workers can finish those tasks at the same time to do it in parallel. To give a concrete example, there are many chairs in this rotunda, and we could imagine sending some person to clean each chair one by one. And there's many chairs in this rotunda. It might take a very long time for a single person to go around cleaning the chairs in the rotunda. But if each of you were to have a brush and were to stand up and clean your own chair, you would find that it would actually take very little time at all. So this is a type of task that is called embarrassingly parallel. It can be the task of cleaning each chair can be divided up between each worker. You can assign one worker to one chair, and as a result of parallelizing this computation, doing it at the same time, you can do it much more quickly. However, there are other tasks, there are other objectives in life that don't seem to allow for parallelization. A job is often called inherently sequential if it seems like it has to be done step by step. And so applying multiple workers to it can't speed it up. For example, let's say that we're baking a cake, perhaps to celebrate a thesis defense, which we'll do at 5:30, so to come on back. But say it takes an hour to bake a cake in the oven. It would seem to be the case that 4 ovens can't bake that cake in 15 minutes. And why is that? It's because baking the cake is like a chain of cause and effect. It seems like it can't be parallelized. It seems like we have to start with the batter and then slowly apply heat and chemicals to eventually bake the cake. And if we were to try to apply another worker, another oven, say to get us from 45 minutes to an hour, this wouldn't make any sense, because how could you put a worker to go from step 3 to step 4? It seems like you have to get to step 3 even to start that other worker. So this is an example of a chain of cause and effect, and it seems like it would be resistant to parallelization. It seems like it would be resistant to speeding it up by adding multiple workers to it. And in fact, these chains of cause and effect are everywhere in our daily lives. Some applications would include understanding the talk. You hear the words and you're trying to process and synthesize them. Generating content one at a time. talking. That would seem to be a chain of cause and effect. Updating your state of the world and deciding what to do next. And this fact that these chains of cause and effect are based on a state of the world that then updates gives the name to the statistical models that are used for these types of computations. They're called state space models. So the basic mathematical formalism.
9:30.
Oh, sorry. Do you mind muting? But yeah, the basic mathematical formalism of a state space model is that there's some state that's finite dimensional. Call it dimension D for the purpose of this talk, and it updates over time according to some dynamics function F. So in the case of baking the cake, the state of the cake is the particular configuration it's in, the state of its molecules, and we apply the oven function to that cake to move it from 45 minutes to an hour. So a state space model, there's a state at time t-1, F gets applied to it, we move to state at time t. We can roll this out from some initial condition as sub-0, grade in to denote we know what it is, and we can roll out that state space model evolution over time. Of course, we can include inputs. Inputs are very important, like hearing the words that I'm saying and having those go into your mind. But we can always include inputs just in the function itself in a technique called currying. So I'll often just use the simpler top description throughout this talk. So this is the mathematical formalism of state space models. And indeed, because these notions of cause and effect are so important in what we do in daily life, there are an abundance of models in statistics and in machine learning that can be subsumed by this state space formalism. Today, I will mostly focus on a particular model called recurrent neural networks. These are basically machine learning models of the human brain, where you have some state, that would be, again, that would be the S, and it takes in some sensory information, maybe the words that I'm saying, and incorporates it with the previous state to get the next state. But this is just to say, while I'll mostly talk about recurrent neural networks, RNNs today, these techniques are broadly general across state space models. Now, this all seems well and good. It seems like certain computations are inherently sequential to govern the inherently sequential processes that we see in our world. But the problem is that these state space models that seem to go step by step, they couldn't be sped up by parallelization. And that's become particularly a problem in recent years with the advent of massively parallel machines. So this is a graphics processing unit, also known as a GPU. It has over 10,000 parallel workers on it. So it's great for speeding up processes where there's a lot of computation to be broken up and parallelized. But on these step-by-step models, these state space models, those would appear to be a bottleneck on such a parallel computer. Speed is important. Speed lets you accelerate things. And as a result, this bottleneck started to impede the use and development of these state space models. Probably most famously in 2017, there's a landmark paper, Attention is All You Need. This introduces the transformer model. That's the T in ChatGPT. And in 2017, they basically say recurrent neural networks, again, a type of state space model, a type of these inherently sequential computation. It's been firmly established as state of the art, but it's inherently sequential. It precludes parallelization, and this is a fundamental constraint on its usage. And since 2017, since NVIDIA started producing larger and larger parallel computers, currently becoming the most valuable company in the world, interest in these state space models, like RNNs, began to wane, and there began to be more focus on approaches that were embarrassingly parallel, like cleaning the chairs in this room. Now, there's some important asterisks next to this. It was known even in 2017 that linear state space models could be parallelized. So when we say linear state space model, it just means that the way we get from our state at time t-1 to our next state is by like a linear transformation or just a matrix multiplication. It was known that could be parallelized, and there were a number of very important papers written on that, and many of the authors of these papers are present here today. And the basic idea that let us parallelize these linear state space models was this core primitive in parallel computing called the parallel scan. And the basic idea is like to unroll one of these linear state space models, which is just a bunch of these matrix multiplications. it might seem like it just boils down to multiplying a bunch of matrices together one after the other. And the sequential way to do that would be to say, okay, start with matrix A1, then multiply it by A2, then A3, in an approach that's inherently sequential. But the insight of the parallel scan is that a matrix times another matrix is yet again a matrix. So you can actually execute kind of this divide and conquer approach where you merge neighboring matrices together into kind of like 2-step ahead matrices or 4-step ahead matrices. And as a result, well, you need many workers to do this. You need a worker for each one of these channels. But if you have sufficiently many workers, if you have a very big GPU like what NVIDIA makes, you can do this workflow much faster. You can do it in, if t is the sequence length, you can do it in log t time, i.e. you can get an exponential speedup. So this was very good. This is why these papers on these linear state space models, these linear RNNs, have been so important and impactful. But a natural question is, well, what if we want more expressive functions than just linear? Somehow one of the main punchlines of the deep learning revolution has been that linear models are often not sufficiently expressive. What about nonlinear SSMs? What about that whole battery of examples we opened with at the start? We'd like to apply parallel compute to those as well. So it turns out people have been working on this for quite a long time. There had been 50 years of work of this in the applied mathematics literature. But it really only got noticed around 2023 in the machine learning context with this really wonderful algorithm jointly, in some sense, rediscovered, but jointly discovered by Lim et al. And Daniele et al. And they call this algorithm DEAR, differential equation as fixed point iteration. And the basic idea of DEAR is going to parallelize nonlinear SSMs. That's the goal. This thing that was believed to be impossible to parallelize, DEAR will parallelize that. And the way it does it is via a parallel iterative evaluation. We start with a guess over the entire sequence length. We kind of make a guess for the entire trajectory. It'd be as if we made a guess for the entire evolution of the cake in the oven. Put atoms in random places. And then at every step, we're going to iteratively refine it. We're going to refine it with this delta S to get to some other guess over the entire sequence length. And each one of these guesses is denoted by a superscript. So we start with superscript 0, then we get to superscript 1, so on and so forth. Each one of these steps is going to use that parallel scan algorithm from the linear RNNs. So we'll involve parallel compute over sequence length. And this basic idea of parallel iterative evaluation is what lets DEAR parallelize nonlinear SSMs. But looking at this, there are a number of limitations that are immediately apparent. One is, wow, we're going to make a guess over the entire sequence length. That seems like it's going to take a lot of memory. Seems like it's going to be a lot heavier than just rolling out the function sequentially. And then also, what's the deal with this iterative business? Do we know if it's ever going to converge? Is it going to converge quickly enough for it to make us worth our while? Is it going to converge quickly enough to be faster than sequential computation? And indeed, when DEAR first came out, it struggled with these issues. It struggled with scalability. We want our algorithms to work with really big data, with long sequence lengths, with big state sizes. And the original DEAR formulation struggled with that. Struggled with stability. There are certain types of problems where it might go all over the place. It might be as if the cake spattered outside of the oven en route to cooking it. And it didn't really have provable guidance as when to use. It wasn't clear when these iterative techniques would converge, if they would converge at all, or if they would converge quickly. So in some sense, what DEAR was doing was it was applying parallel compute to a problem in dynamics. And like I said at the start, there are going to be 3 ingredients in the talk. There's going to be parallel compute, there's going to be dynamics, and there's going to be optimization. And indeed, the solution, my contributions in my PhD, which I'll spend the rest of our time discussing, is to solve these problems, the scalability, the stability, and the guidance on how to use this with techniques from optimization. So we'll bring in optimization techniques to apply parallel compute to problems in dynamics. I'll talk about 3 papers in particular. One is where I will extend the original DEAR to a larger family, including scalable variants called quasi-DEAR, borrowing from the quasi-Newton notion in optimization, as well as more stable variants, which has this very convenient acronym ELK. So as a result, we call this broad family of methods the ungulate family. An ungulate is a large hoofed mammal, like a deer, or an elk. Secondly, once we've made it scalable and stable, there's a natural question that means like, when will this actually give us speed ups? So again, borrowing from the optimization toolbox, I provide provable guidance on when this iterative approach will converge quickly. What types of dynamical systems can we parallelize, and what types of dynamical systems can we not? And then finally, I'll not only connect our ungulate family to other techniques, I will provide guidance on which ungulates, which members of our family to use in what settings. So these are the three main papers I will discuss in this talk. And the broad outline will be, I'll provide a little bit more background on this DEER technique, which will be the basis for the rest of this talk. Then I'll talk about those three papers, methods, theory, and the combination of them. And then finally, I'll conclude with some brief remarks about the future. So let's get started. So again, just to ram this home, here's a demonstration where we are going to parallelize a state space model of a sequence length. The gray trace is what the true sequential rollout will be. That's the target. And the left plot, when I hit play, we'll see the true sequential approach slowly roll out, step by step. Meanwhile, on the parallel side, parallel is going to be in blue. We've made this messy guess over the entire sequence length. It's completely wrong. The blue is not matching up with the gray at all. So, by analogy, this is our totally wrong initialization of the cake in the oven. And what's going to happen is when I press play, we're going to go through multiple of these parallel iterative steps. We're going to act on the whole sequence length, and we're going to get closer and closer to the true gray rollout. And in around 4 of these parallel steps, we will converge. So here we're playing it. Sequential is going through. And by 4 iterations, we're done. Now, of course, we're acting over a whole sequence length. So each parallel iteration takes longer. It takes around 6 of these sequential steps. But still, when it's all said and done, this parallel approach gives a 4x speed up in this example. And on longer sequence lengths in this talk, you'll see even more dramatic speed ups. So let's go into the details of how is this technique to parallelize things that would be slow and would seem to be inherently sequential. Let's talk about the mathematical foundations, and in fact, the optimization foundations of how we do this. And indeed, that's the basic idea. We go from sequential evaluation, from dynamics, to optimization. And the basic idea is we want to find a sequence of states that satisfy our state equation. That's our state, time t minus 1. That's the state it's going to go to. And we're going to put these stars next to them to indicate that that's our goal. And we could do it step by step, kind of in the dynamics perspective, or we could just say, okay, this is some very high dimensional object, and that's this bold S star 1 through t. So the 1 through t is denoting that that's our guess over the entire sequence length, or sorry, that's the true rollout over the entire sequence length. Now again, in this optimization perspective, we could make a guess, superscript 0, which would be our wrong guess over the entire sequence length. And again, what's the point of making this wrong guess? It would be, we could do it completely at random. It would seem to have no relation to the dynamical rollout. And the core insight is that we can measure how wrong it is. We make a wrong guess as superscript 0, but we measure how wrong it is. And how do we do that? We use the state space equation. We can define this one-step prediction error, R, or residual, where we just say, look, what is the state at time t minus our dynamics function applied to the state at the previous time? If we were dealing with S star, this would have to be 0. Because literally, the true dynamics equation is that when we apply F to S star at time t minus 1, we get S star at time t. So if we were plugging in S star, there would be no prediction errors. It would correctly say, you're perfectly at S star. But since instead we're starting with this random guess, this S superscript 0, this is non-zero. It's giving us an error signal. If we square them and sum them up, we now have an optimization problem. And we naturally, now it's very clear what we want to do. We want to start descending on this optimization landscape, and we want to try to get to S star. And once we get to S star, we'll have the true sequential rollout. So this is how we go from sequential evaluation to optimization. But the natural question remains is, there's many optimizers out there. Which optimizer should we use to leverage parallel compute to converge provably and to converge quickly? So what DEER uses is Newton's method. DEER is fundamentally Newton's method. Just merge them in your head for the rest of the talk. And Newton's method is a workhorse that is fundamental in introductory calculus. So just as a review, what Newton's method does is it provides a way for us to find zeros, solutions of nonlinear functions. So this is just in one dimension. We have one-dimensional S, and the function is R of S in one dimension. And we want to find the root, the solution, the zero of this equation. We want to find S star. Again, we make a random guess as 0. We don't know where S star is, so we make a guess as 0. And it's wrong. It's not the true solution to this function. But as we said before, we can evaluate this function. We can get R of S0, and we can measure that non-zero residual. And then what Newton's method does is it takes this function, it takes our guess for it, and it linearizes the function. Instead of having this curvy function, it draws this straight line in blue. It linearizes the function around our guess, and then it evaluates to get a new guess S1. And then all Newton's method does is it iteratively does this approach of linearizing and then evaluating, and then linearizing again, and then evaluating again until convergence to S star. So this is Newton's method. It's been a workhorse for quite a long time. And all DEAR is Newton's method, but applied to state space models. Again, here's our rollout of our state space function. Again, following our dynamics function, which takes a state that's d-dimensional to another state that's d-dimensional. Again, it seemed like the type of thing where we had to roll it out one ball at a time, one state at a time. And instead, what DEAR does, what Newton's method does, is it takes well, first off, we make a guess. We make a guess over the entire sequence length. So here I've replaced it with these superscript i's. That gives us our one-step prediction error, that error from the previous slide. And then what we do is we take that nonlinear function and we linearize it. We take the derivatives. So the idea is that each DEAR step uses this linearized dynamics function, which is just the first order Taylor expansion. And that's the DEAR step. So each step of DEAR takes what used to be a nonlinear state space model and turns it into a linear state space model. That's the DEAR equation. Again, it's a linear dynamical system. So A is a matrix, and it's acting on our state to get to our state at our next time. And the point is, because each DEAR step is linear, we can use that parallel scan. We've effectively taken nonlinear SSMs and put them into the regime of the linear SSMs. So yeah, this is our parallel scan, a review from the start. But the point is, with many parallel workers, we can evaluate each DEAR step in time that's logarithmic in the sequence length, much faster than rolling it out step by step by step. So this is great. So in an algorithm block, just to review, DEAR is an algorithm block. We give it our dynamics function f. That's what takes us from state to state. We give it our initial condition S0, that guess over the entire sequence length. And then all we do is iteratively, we linearize that function. We can do that for everything in parallel. And then we evaluate it using that parallel scan. So each one of these steps is only log t in time, which is much better than what would it take to roll out the whole sequence, which would be length t in time. And we just do this iteratively. And each one of these steps of linearize and then evaluate, that's equivalent to 1 Newton iteration. So this kind of concludes my recap of DEAR, the foundations. And the basic takeaway is that Newton's method lets us use the thousands of processors on a GPU. It actually lets us put them to work to parallelize and therefore accelerate what would seem to be inherently sequential computation. Put another way, I believe that if Isaac Newton were here with us today, he would join us in saying, haha, GPUs go burr. Okay, so that's DEAR. That's the fundamentals we will be building on. Now we're going to transition to my contributions. How have I built on DEAR? How have I improved our usage of DEAR? And again, there's going to be 3 main papers I'm going to talk about. Methods, where we generalize it to approaches that are more scalable and more stable. I'll provide theory. I'll say when we can parallelize. The punchline there will be that somehow properties of the dynamical system we're trying to parallelize determine its convergence. And then finally, I'll conclude with our third paper, which is a bit of a combination, where I prove how the particular nature of the particular ungulate we use controls its convergence rates with the guidance that you should use the ungulate that's best suited to the problem. So those will be the three papers I discuss in this body. And let's dive into them in more detail. So the core idea is that DEAR had scaling limitations. It was bad in long sequence length or large state size settings. It fundamentally did not work very well in big data regimes. And we can just see that from that DEAR equation. So here's that dynamical system that is DEAR. And the point was we wanted to linearize. And when we linearized, we got this A matrix. This is A sub t. It's the derivative of f with respect to s. It's a Jacobian matrix, and it's dimension d by d. So already you look at it and you say, wow, like if d is really big, this actually requires a lot of storage. Plus, we're going to have to do it over the entire sequence length. So consequently, the original DEAR method had very large, prohibitively expensive memory and compute costs. It didn't scale well. Now, there's a lot of literature out there in optimization on quasi-Newton methods. It's known that Newton's method doesn't scale well. So the question is, how can we cook up a quasi-Newton method that will still work with our workhorse for parallelization? Because our goal was to parallelize. So we need some sort of quasi-Newton method that will play well with the parallel scan, that approach we use to merge neighboring matrices together. And the parallel scan works when you have elements that combine and stay in the same class. A matrix times a matrix is another matrix. That's why the parallel scan works with DEAR. We needed some other object that would compose nicely, be closed under composure. And a simple example is actually just diagonal matrices. So a diagonal matrix times another diagonal matrix, it remains diagonal. There's fewer elements. It's reduced by a square root. It's only d-dimensional instead of d times d-dimensional. And consequently, it has much better scaling properties. So this is a clear thing to try. But to anyone who has either worked in optimization or dynamics, it seems like a total hack. One would do this and would say like, will this really work? Would this even get to S star? Would this even get to our true minimizer? And it turns out that yes, I proved that it can. I proved that DEAR and quasi-DEAR, and in fact, any approximation we wanted to the Jacobian would actually converge, and in fact would converge globally. We could make our initial guess anywhere. This is again non-standard. Typically, Newton's method is very finicky. It depends on where you want to start the initial guess from. But I'm actually claiming that these approaches will globally converge. The way I prove this is with induction. But we can actually prove it in the GIF. The basic idea is that we know our initial condition. We know our starting point S0. And every turn of the crank of this DEAR or quasi-DEAR approach will always give us at least one more step right. So as a result, no matter how we initialize, no matter what our original red guess was, we will eventually converge in at most t iterations. So what's going to happen when I press play on this GIF is, again, right now, the true sequential rollouts in gray, that's our target. We have this red initial guess, which is completely wrong. And then when I press play, as soon as the red becomes the true sequential rollout, it will turn green to denote that it's converged. And when I press play on this GIF, you will see a wave of greenness go from the initial condition S0 all the way to the end. So let's press play. So you see that we're always getting at least one more step right at every turn of the crank of this DEAR approach. Now, converging in t iterations, this guarantee of global convergence is a great thing to have. Having worked with approaches that are not globally convergent, I can say it's a lot better to work with something that's guaranteed to converge. But still, t iterations would be the same as rolling it out sequentially. So while this is a nice guarantee to have, it's not good enough. So the question is, how fast will this quasi-DEAR approach actually work in practice? So we ran a bunch of experiments. Here's one of them. So we trained an RNN, again, this type of state space model used for deep learning. We trained it on a really long task in computational neuroscience. So this was a sequence length of around 18,000 individual time steps. So this is a type of task that's designed to be hard for an RNN to train, because again, previously it was believed that RNNs were inherently sequential. So a really long sequence length would mean it would take a really long time to roll it out. So here we show how long it took to train to given train accuracy. So what we did is I ran sequential for 24 hours, and then I just gave up. It was at around 70%, 75% accuracy on val. It was just taking way too long to converge. Meanwhile, with Deer in red, I could train it in 11 hours. And with Quasi-Deer, I could train it in 4. So Quasi-Deer is empirically demonstrating on a real task, on a real benchmark, a 3x speed up over Deer and at least a 10x speed up over Sequential. So this is to say that Quasi-Deer really can work and really can accelerate our ability to train state space models that we care about. But Deer and Quasi-Deer don't always work. So here, we're actually trying to get Deer and Quasi-Deer to do a pretty simple task, which is just to recapitulate a sine wave. That's the dotted line that's oscillating. And you see, as we try the Deer and Quasi-Deer traces, it's literally going off the charts. Deer is going off the charts there. Quasi-Deer is going off the charts there. It's being very unstable. And this, again, is no surprise to folks who've worked with Newton's method and optimization setting. It can be unstable. And when it's going off the charts, basically what it's saying is the update step, the delta S, that takes us from one guess over the whole sequence length to another guess over the whole sequence length, is just becoming too big. So once again, going to the optimization toolkit, there are techniques to deal with this. So ELK, which I talked to you about earlier, it wasn't just a ploy to put in a friendly animal. The letters actually have meaning. It stands for Evaluating Levenberg-Marquardt with Kalman. And it's a unification of techniques from optimization with techniques from dynamics. So we'll start with optimization. This is the Levenberg-Marquardt method. And again, we're trying to optimize some sort of landscape. We're trying to get to our minimizer S star. And we're currently at our point SI. That's our guess after iteration I. If we take the undamped Newton or Deer update in red, we might go way too far. We might be unstable and go in the wrong direction. So what trust region, Levenberg-Marquardt, says is restrict your update to a ball, a trust region, where we trust basically our linearization, our approximation for the loss function. So as a result, the step in this setting is smaller, it's more stable, and it's actually getting us toward the minimizer. So there's a clear technique from optimization, but how are we going to port this into dynamics? And how are we going to port this into dynamics in a way that remains parallel? So this is where Kalman comes in. So the Kalman smoother, it's a workhorse in dynamics, basically to figure out where something that's evolving is if we get readouts from it. So somehow, like the standard example is always like you have an airplane or you have a spaceship and it's flying in space, and you know how it's evolving over time. In this setting, it's going to evolve linearly because our Deer steps are linear. But what if you get updates from it? What if you get updates from it over time? Those updates kind of stabilize your best guess for where that state is, and therefore restrict the dynamics. It's not just the dynamics running on its own, they're being stabilized by your observations from them. So this is the Kalman smoother. It's often used in dynamics for this purpose. And the point is that we can kind of port over Levenberg-Marquardt into this Kalman setting by setting our observations to be our current state. As a result, it means that ordinarily we would just run the linear dynamical system, the linear state space model that is Deer. We just run it forward. But now with ELK, with this Levenberg-Marquardt / Kalman smoother interpretation, we use the current state to damp it, to make it not take as big steps. It turns out that Kalman smoothers can also be parallelized over the sequence length, which is what gives us the ingredient of parallel compute. So when we try it out on that pesky sine wave, our undamped methods, Deer and Quasi-Deer, they're in red because they're fiery and they jump out of the plot. Our damped methods are ELK and Quasi-ELK. Quasi-ELK is just the scalable version of ELK. They're blue because they're regularized and they're more stable. And you can just visibly see that the damped methods of ELK and Quasi-ELK are staying closer to the sine wave and they're converging more quickly. So this is to say that ELK improves the stability of these parallelization, these ungulate techniques. The bummer is that we still can't beat sequential. Our goal with these techniques was to be fast and sequential. And while we often are and will be for most of this talk, on that particular example, I wasn't able to get it to be faster. Sequential was computing in around 100 milliseconds and Quasi-ELK in around 200 milliseconds. So this is what motivated my theoretical contributions, which was, are there limits to parallelizability? Are there certain dynamical systems that really are inherently sequential, and how can we formalize that? And the punchline for that setting, for the paper I will go on to discuss, is that it is the dynamics that determine the convergence properties of our ungulate optimizers. So again, we need to answer this core question of how do we know when our optimizer will converge quickly? And the point is, we'll connect the notion. I'll formalize these shortly, but we're going to connect the predictability of those dynamics to the difficulty of that optimization problem. So again, here, the top row will be our dynamics perspective, and the bottom row will be our optimization perspective. And the basic idea is, for a dynamical system, we can divide it into predictable dynamical systems or unpredictable dynamical systems. In a way that I'll make more formal, the predictable dynamical system means, hey, if you get a small perturbation, it doesn't matter too much. They still more or less end up in the same place, meaning that you can use nearby observations to help predict in the future. An unpredictable or chaotic setting is where you have small perturbations and it makes a huge effect. So this is why it's so hard to predict the weather. There's something called the butterfly effect, where if a butterfly flaps its wings in Brazil, you get a tornado in Manhattan. The basic idea is that when we do this trick, when we go from dynamics to optimization, it's the predictability of that dynamical system that governs the qualities of that optimization landscape. When it's a predictable dynamical system, we'll define a suitable notion in which that optimization landscape is well-behaved and bowl-like and easy to optimize. And the unpredictable one will be narrow and jagged and hard to optimize efficiently. So let's formalize these notions. So to formalize this notion of predictability of a dynamical system, we use this concept of the largest Lyapunov exponent, which I'll abbreviate as LLE, or in math, lambda. And the basic idea is this LLE quantifies how a small perturbation, here's one perturbation for blue, here's another perturbation for red, does it grow or does it get crushed out? And the basic formula is that perturbations evolve as e to the lambda t. The idea is that when you have predictable dynamics, where this largest Lyapunov exponent lambda is less than 0, small perturbations are getting exponentially crushed out. And when you have chaotic dynamics, they're getting blown up. So this is how we will define predictability. And we got to link it to some notion of optimization difficulty. Now I'm in the room with Professor Boyd, who's an expert on convex optimization. It turns out that the loss function isn't always convex. But what I was able to prove is that it satisfies a weaker condition called PL. And the PL condition is this equation at the bottom. It's often known as gradient dominance. And the basic idea is we need somehow a function is PL if its slope, like this thing that's sending out the steepness of the function, is sufficiently large when we're in some sense at high altitude. So a really flat function has a very small PL constant mu. That means it's super flat. It means we don't have good gradient information far away from the basin. On the other hand, if a function is nice and bowl-shaped, easy to optimize, we have great gradient information even when we're far away from the minimizer. So the whole project will be to bound this PL constant, this difficulty of optimization, in terms of that LLE lambda, which told us something about the predictability of the dynamics. And that's my main contribution of the second paper, where again, this mu is the difficulty of optimization, and we sandwich it in terms of the predictability of the dynamics. You see lambda on both sides. And that's the core result. It's that the predictability of the system, as measured by this Lyapunov exponent, determines how well we can optimize it, and therefore how easily we can parallelize it. This plot on the left, it's just this theorem shown again as a picture. The dotted line, that's LLE equals 0. That's the boundary between predictability in LLE less than 0 and unpredictability, chaos, LLE greater than 0. And what we're showing is that when we make our sequence length arbitrarily long, set it to really big, if we're in a predictable setting, mu converges. It becomes some non-zero value. So it's basically saying when we're predictable, our optimization landscape never gets too badly behaved. It's always nice and bowl-shaped, no matter how long we make the sequence length. On the other hand, when we're unpredictable, we can see that this PL constant mu is going to 0 super quickly. It's going to 0 exponentially quickly. As a result, that's saying that when we're trying to parallelize an unpredictable setting, We might say, well, like really long sequence length, that should help us parallelize. But it's basically saying like, no, like the longer we make our sequence length, the flatter and flatter that landscape becomes, the harder it becomes to optimize and the more steps it takes to convergence. So this is what I proved theoretically. And then I also validated an experiment. So I found one of these Thesis models where I could control that largest Lyapunov exponent by tuning a parameter. So it's basically, again, I'm just making the system more and more unpredictable. Again, the dotted line to denote the boundary between predictability and unpredictability. And what we see on the left plot is the number of steps to convergence for many different optimizers, including Deer and quasi-Deer. And for all these optimizers, we're seeing that as we increase the unpredictability of the system, the number of steps needed to converge is just growing. It clearly grows with the chaos of the system. And then on the right-hand side, I'm showing the wall clock time on a GPU. So sequential is green. It takes pretty much the same amount of time, whether the dynamics are predictable or unpredictable. But we're seeing that the transition, when it stops making sense to parallelize, is happening right at this boundary between predictability and unpredictability. So this is why the title of the second paper is Predictability Enables Parallelization. Okay, so just to take stock of where we've been. I introduced a bunch of methods, Deer, quasi-Deer, elk, the ungulate methods that let us broaden and extend our ability to parallelize sequence models. And I proved generally, what are the types of sequence models that we can try to parallelize? And the natural question is, okay, how can we combine these? How can we use the fact that quasi-Deer, for example, was an approximation technique? Will that impede its convergence rates? Or is there a way to say this precisely? Is there a way to know when I should use Deer, when I should use quasi-Deer, when I should use other ungulates? And that's exactly the question that I tackled in the third paper. So the first step of the third paper was actually going out into the wild and finding other ungulate friends. And the core point was that different linearizations of the dynamics actually, they can generate Deer or quasi-Deer, but they can also generate other well-known methods in the literature. So again, this is our update equation. It's this linear Thesis model. And in general, we're plugging in some A tilde to approximate the linearized dynamics. If we use the true linearization, that'd be Deer. If we use the diagonal, that'd be quasi-Deer. And it's a very natural question to ask, what if we start plugging in even simpler linearizations? And the first thing we found is that actually, when we plug in even simpler linearizations, like the identity matrix, basically just means multiply by 1, that actually gives back a very common method in the literature called Picard iterations, which has been used to parallelize diffusion models recently. If we go even simpler and we plug in 0 for that linearization, that actually gives back Jacobi iteration, which is another workhorse that has been used to, for example, in a technique called parallel decoding. So the first contribution to this paper is to broaden this ungulate family to include not only methods I developed, but also ungulates that we found along the way. But okay, so now we have these different techniques. And the question is, where should we use which one? Why is the diffusion modeling literature using Picard iterations? Would it work well for a recurrent neural network? How do these different ungulates? How well do each of them work when we set them to work? And our core notion is I'm actually able to prove a convergence rate for any member of the ungulate family. And the basic punchline is that any ungulate I give you will converge with at least a linear rate gamma. First, let's unpack that. What do I mean by linear rate? Linear rate's a term from optimization, and it basically means exponential decay. It basically means that the error factor, like the error we have, our error in approximation, it will decrease by a factor of gamma with every step. Every turn of the crank will reduce it by gamma. That is exponential decay. To try to illustrate that, here I'm using Jacobi iterations to parallelize a linear SSM. And I'm plotting the error on the y-axis it's what's called log scale. That's kind of like the Richter scale. So each tick is actually divided by 10. And when I plot the linear rate, when I plot the trajectory of the error, these are for the different colors are different linear Thesis models. We get a line, which on log plot is equivalent to exponential decay. So this is demonstrating that, for example, in this setting, Jacobi iteration really does have linear rate, and it's trying to illustrate like what is linear rate? What is exponential decay? The other point of note is, again, we said that Jacobi was linearizing the dynamics by setting them equal to 0. And what I'm plotting with the different colors denote is what the real value of the matrix function is. So somehow when it's 0, you get a really steep line for fast decay. That means gamma's close to 0. That smaller gamma means you're converging faster because you're reducing your error by a larger factor with each step. But as I make the true dynamics very different from the approximate dynamics, i.e. by increasing it in red, we're seeing that the rate of decay is slowing down. It's becoming flatter. So this figure is prefiguring the analytical result, which it breaks down this linear rate. So this linear rate gamma turns out to be a combination of the predictability from the second paper, as well as a notion of how good of an approximation is that ungulate method. So again, this is our linear rate gamma. Smaller is faster. It means we're reducing our error by a more aggressive factor at each step. We need gamma to be less than 1 for this to even be meaningful, for this to give a guarantee that the function is that the error is decreasing. And let's just kind of look at the numerator and the denominator to better understand how approximation error and predictability impact the linear rate. So again, this is the approximation error of the ungulate method. That's the A tilde denoting the approximation to the true linearized dynamics AT. And this is basically saying if there's a big error, gamma gets big, so we slow down. On the other hand, this mu tilde, that's a callback to the PL constant from the second paper. It's a notion of the conditioning, where somehow 0 is maximally unpredictable for the ungulates, and 1 is maximally predictable. So this is saying that if we're dividing by something, if the ungulate we choose, if the A tilde we choose gives rise to a very unpredictable system, we will pay a penalty, and gamma will get bigger, and our convergence will slow down. So just taking a step back, this is a theoretical result, basically giving us a control of how quickly each of these ungulates will converge, and also suggesting the guidance that we should use whichever ungulate method is a good approximation to the true dynamics. Not only prove this, but again, demonstrate this in simulation. Here's a simulation where the true dynamics are quite close to 0. I'm plotting the Jacobian of the dynamics here, and it's the plot range is from -1 to 1. So you can visually see the colors are pretty pastel. This is basically saying that the Jacobian is close to 0. And when we look at the number of Jacobi iterations in black, that's again approximating the Jacobian by 0. We see that we don't need very many fixed point iterations to get good convergence. On the other hand, Picard in brown, which was approximating by 1, needs a ton of iterations. It's basically just as slow as sequential. Meanwhile, quasi-deer and deer are converging quickly. On the other hand, if we switch to a setting where the dynamics are very close to the identity, again here we basically have the strong diagonal of all ones. Now the roles between Jacobi and Picard are flipped. Now Jacobi is it's just as slow as sequential. As a result, it's slower to run in terms of wall clock time, while Picard is more competitive and doing better on wall clock time. Meanwhile, throughout in both settings, you see that quasi-deer is a very nice method that's robust in both settings and is giving around 10x speed up vis-a-vis sequential consistently. Okay, so this concludes the contributions I'm presenting, my 3 papers. And again, just to recap it, I started out with a methodological contribution where I took deer and I made it more scalable and stable, opening up a whole family of ungulate methods, including quasi-deer and elk. Applying these to different techniques resulted in the natural question of, when can I actually hope to get a parallelization speed up from applying these ungulates? That's where the second paper, my theoretical contribution came in, where we showed that it was a property of the dynamical system, its predictability, that allowed for an ungulate method to achieve speed up. And then finally, in the last paper I just presented, I combined them by providing convergence rates for all the ungulates, both those that I created and some of those that we discovered along the way. So yeah, this concludes my 3 papers, the methods, the theory, and the combination. And now I'll provide a brief prospective for the future. So again, why am I so excited by these ungulate methods? The core idea is that they bridge models to hardware. As we started at the beginning, sequential models are everywhere. In our daily lives, we go through sequences of tasks. We put on our socks, then we put in our shoes, and then we advance from there. And we, of course, have tons of statistical models that are designed for these sequential settings. However, the fastest and most powerful hardware that exists today are these parallel machines, these GPUs that make NVIDIA the most valuable company in the world. These sequential approaches might seem to be bottlenecks on parallel hardware, which is why they were being deprecated. These ungulate approaches let us parallelize these inherently sequential models. They help us bridge from important classes of models to the best hardware that we currently have. And indeed, this is a wonderful thing to have. And consequently, my work on quasi-DEER has inspired some very large-scale and compelling follow-ups. One of those I did inside the lab with my collaborators, David Zoltowski and Skylar Wu, where we took a different type of state space model. This is called Markov chain Monte Carlo, and accelerated it via these quasi-DEER approaches. So MCMC, it's a workhorse of Bayesian statistics. It lets us figure out solutions to complicated models. And we used many of these. We showed it in many different examples in the paper. But our larger scale experiment involved taking one of these probabilistic models that The Economist uses to try to aggregate polls to predict the outcome of presidential elections. So here, this is a very big scale regime. The dimension of this MCMC chain, the state size is around 5,000. So we had to use quasi-DEER. And when we deploy it, we're able to see an 8x speedup of our parallel methods over sequential methods, whether they're run on GPU or even on a CPU, which is supposed to be faster weight to run sequential approaches. Meanwhile, in work beyond our own lab, in work that I was not even involved with directly, Federico Danieli and his team at Apple took quasi-DEER one step further and actually took some RNN models and not only used quasi-DEER, but actually just made the whole RNN have diagonal dynamics. With these approaches, which he calls para-LSTM and para-GRU, he's able to train 7 billion parameter language models, which is no small feat, and achieve very comparable language modeling performance to what are state-of-the-art methods for large language models. So all this is to say that even though quasi-DEER might sound small in its name, it's had very large-scale impact already. And thinking more broadly, I think the possibilities for impact are even larger because, as we began at the start, state space models truly are everywhere. We've mostly talked today about recurrent neural networks and Markov chain Monte Carlo, but there are many, many applications that you can see on the board and that I'm sure you can think of in your own research in your own lives. I think it'll be extremely exciting to continue letting the ungulates roam free, to apply them to these different models, to sort out the methodological challenges that will arise as we expand the scope. But I think in sum, the future is very bright for ungulate fans and for parallelizing inherently sequential computation. Thanks very much for your time, and I'll take some questions. Gabe? Oh, thanks. It's a little hard to hear sometimes, so we'll go mic questions.
Yeah, have you considered doing this on an irregularly spaced time grid?
Yes. So in some sense, you could just change. So that's the line that's solving differential equations. So yes, that could immediately be done.
Can you just go back one slide, please? The one with the perplexity, with the plus thing. Yeah, that one. I'm a little unclear why the larger model size has lower perplexity.
Lower perplexity is better.
Right. But okay, but you're able to get that with a larger model size.
Yeah. I think this plot is mostly meant to show the kind of a scaling law. So here, like the 1 billion parameter model is around perplexity of like 13, and the 7 billion parameter model is around perplexity of 9. So, I don't even know how large the current large language models are, but like the promise is that if we were to keep scaling up these RNN approaches, we would get lower and lower perplexity, is what this plot is trying to suggest.
Thank you.
Start over here.
Can you go to, I think it was like slide 45 or so? I think you had like the result that was like, actually, sorry, go for it a little bit. This theoretical result, can you give some intuition for how like you derive this?
Yeah,
where this comes
absolutely. So the basic idea is when we run Newton's method, we are linearizing those dynamics. This can give rise to a really big Jacobian matrix. And the core idea is that it turns out rather intuitively that the PL constant mu, like that's characterizing somehow the conditioning or bowl shapedness of the optimization landscape, is linked to the conditioning of that big Jacobian matrix, which is basically the ratio of its largest singular value to small singular value. So the name of the game becomes, if you look at that big Jacobian matrix, can you control its condition number? It turns out that that big Jacobian matrix has a lot of structure to it. It has this block bidiagonal structure that lets us basically prove, so that big Jacobian matrix has this block bidiagonal structure. So it's all, basically the point is like, because again, we're having this Jacobian act over the entire sequence length. So the dynamics function is S minus F. So when we take derivatives, we get all identities on the main diagonal and all basically the time-stepping Jacobians on the lower diagonal. So as a result, the structure lets us start to prove results about it, is the TLDR.
Gotcha. One other quick follow-up. On the slide that you showed with the results, like the perplexity results, I guess I'm curious, like have you done is there any way to like measure what the predictability of like language model or like that space of models are and what that looks like if it performs, comparably well to sequential methods?
Yeah. So predictability can be measured numerically. I haven't done it in this setting, and I don't think Federico has. But basically, like in this setting, the parallel STM and para-GRU were converging in like 3 Newton iterations. And the way they were doing this is they were clipping their weight matrix. So it's basically a certainty that they were in the predictable regime.
Sorry, I had a quick question about, you said you used Deer and Elk to train RNNs. I'm just kind of curious. It seems like Deer and Elk are methods for like, getting predictions from state space models, but not ways to estimate parameters. I'm just kind of curious. Do you mean that like, you're doing regular parameter estimation, back propagation, whatnot in RNNs, and then anytime you need to evaluate it, you used Deer or Elk?
Yeah, no,
Is that what that means?
That's an excellent question. So yes, the point is that when you train an RNN, you need to do a forward pass, and then that gives you your error signal. It tells you how wrong you were, and then that error you send it back through time with the backwards pass. So the issue is you can't do a backwards pass until you run a forwards pass. So previous approaches that were trying to do the forwards pass sequentially, it meant that you didn't get many shots on goal. Like it took a long time to get each gradient update. So what Deer does, as you point out exactly, Deer and quasi-Deer and all the ungulates, they parallelize and therefore reduce latency of the forward pass. So your intuition is absolutely right. It's a forward pass acceleration technique, but by speeding up the forward pass, it means we get to take more backwards passes as well. So that's how it accelerates training. And then the other point is to say that why the ungulates merge so nicely with training RNNs is because the backwards pass is also a linear dynamical system. Like, so kind of what we're doing is we're doing many linear dynamical systems iteratively to get the forwards pass, but then we can reuse those Jacobians for the backwards pass. And that backwards pass can also be computed in parallel with the parallel scan trick. So you can also like, we wouldn't call it Deer, but we can also parallelize the backwards pass with this exact same trick.
Okay, thank you.
So Javier, you're always positive and optimistic. You listed off all these different applications, and then you showed us an chart of RNN where like Mambo is outperforming things. I'm curious, like of these applications, if I don't know what my Lyapunov exponent is for my given problem or something, what's your general guidance or intuition about what this will actually end up being used on? Like what if you were to join a team and they were like, Javier, we're going to bring you in on this problem we have, and you're going to get a 1-year equity cliff and everything. Like, we need you to solve this with your method. What would you say? Like, I don't think this is going to work for that.
Yeah. So, I mean, somehow like the notion of, yeah, that's a great question. And in fact, that's exactly what I'm being asked to do at Unconventional. So, so you said it very well. First off, like somehow like chaos is a pretty like, well-defined notion. So like broadly speaking, like I think there is intuition for when a system will be chaotic versus predictable. So like the easy one would say like, no, like I would not apply state-space models to settings that are known to have chaos or known to be chaotic. What we found, I think this goes really nicely with the CMC example. I'm not sure. Let me see if I have backup slides on this. But what I'd say is that these approaches work really well when you somehow have modal behavior. So by this, I mean, like, if there's some notion in which states are going to sync to a certain place, like if you're going to visit certain places more often in your trajectory, then that will be like predictability. So for example, like it was a bit of a surprise to us that the ungulate methods worked so well on Markov chain Monte Carlo. And why is that? Well, Markov chain Monte Carlo is a way to explore a probability space, and you want to go to the places with high probability. So what Markov chain Monte Carlo is going to do is it's going to keep pushing you towards the areas with high probability and away the areas with low probability. As a result, in those regimes with high probability, you're going to start pooling there. In other words, you're going to contract or have small perturbations get crushed out as you move towards those modes. So I think that's kind of a nice, theoretical explanation for why the ungulates have actually been so successful in the setting of Markov chain Monte Carlo. I think another setting where you naturally have this pooling behavior is actually potentially in reinforcement learning, where presumably you'll want the state of your agent to explore regions with high reward vis-a-vis low reward. And actually, like, I think I just found out about like a week ago, but it turns out that Jan LeCun has come out with a paper where he parallelizes reinforcement learning via this optimization perspective. It doesn't have DEER inside of it, but I think it's an extremely promising area to explore in the future.
We'll do one more question.
Thanks, Avi. Great talk. My question is kind of also piggybacking off that a bit. For the theory part, this is a really interesting result. Do I understand correctly that kind of the result and also the experiments are suggesting that like predictability is like necessary for fast convergence of the parallelization?
Yes, I would say so.
Then a follow-up I'm curious about is like, could there be a way to like, or do you think there could be a way to like predict the predictable parts of the trajectory? Like, I guess that necessity is if you want all the states, like all the activations, but if you're doing inference or something, like, and you only care about the last one, could there be a way to speed things up by computing adaptively with the parallel methods?
You're saying like sometimes use parallel and sometimes use sequential? Or?
Somehow, yeah.
Yeah, no, I think that's a great idea. I think it's a great idea, and I'd love to explore further. So yeah, great instincts.
Thanks.
Let me hand it back to you, Javier.
Yeah, I'll do some brief acknowledgements. Yeah, first off, just want to thank my committee. Sorry that we're running over time, but thanks for being here. Emily Fox on Zoom. Actually, a lot of these ungulate methods started in a reading group we did. It was very different, but it was on temporal point processes, and it's been wonderful to see it evolve. Chris Ray also calling in from Zoom. It's been wonderful working with your students, Kelly and Jerry, and of course the work your lab has done, particularly on deep state-space models, has been a huge inspiration, I think, to all of us in the lab, and in particular to this work. Kayvon, I love taking CS149 from you, and maybe my favorite part was getting to brag to my classmates that my professor was D3 national champion in tennis. Thanks very much for taking the time. And of course, Stephen Boyd, you're an expert on optimization. Thanks very much for coming to this talk. Of course, the biggest thank you has to go to the last member of my committee, Scott Linderman. Here's Scott at a beach party that he helped to organize with Libby Zhang down in Santa Cruz. Thank you for teaching me so much about so many different aspects and always bringing such a kind and cordial and community-driven aspect to the lab. It's made being in Linderman Lab a true highlight of my time at Stanford. Speaking of the lab, so many of you are here today. I just want to say that I often brag to other folks around Stanford that Lindemann Lab has got to be one of the kindest and happiest labs at Stanford. Here are photos of all our adventures together, but thank you, all of you, for making the PhD such a wonderful experience. I have to say a particular thank you to all the Ungulate collaborators, Andy and Jimmy, for bringing me on. You know, this dear work fundamentally builds on your groundbreaking work on S5, and it just wouldn't have happened without you. Scott, of course, for leading the whole way and really bringing the parallel scan into these state space models. To all my collaborators, Leo, David, Ken, Kelly, Hyun, Jerry, Alex, and also ungulates where you didn't get published, Amber, Marin, Nikhil, ENC, and Hansen. Thanks for all of your ongoing work, and I'm very, very optimistic about the future. You know, it truly took a village to work out all of these techniques, but kind of with each of the 4 papers I presented today, there was a particular postdoc mentor I really associate with that paper. So first off, I have to say a huge thank you to Andy. I've told my parents that you've been my guardian angel during my PhD. I mean, truly helping me on, you know, really training me up on the ropes, everything from writing abstracts to making plots to doing research properly. You know, thanks for really kickstarting this PhD and making it all happen. The second paper, Leo Kozhikov, I'm sure you're calling in from Zoom. I'm sorry we don't have a photo together. We basically collaborated entirely on Zoom since a fortuitous meeting at NeurIPS, but your intuition about optimization dynamics has always been spot on, and I've learned so much from both your intelligence and from your generosity. Kelly, where's Kelly? Kelly, it's been a pleasure working with you. I've always been blown away by your brilliance in software engineering, developing, really making research code work at scale. I remember going into your deep SSM code base and being like, holy cow, like this is a different level. The techniques you've taught me, I've used in every single project since. They've been absolutely fundamental, and thank you for so much you've taught me during this PhD. Finally, David, obviously you did amazing work on parallel MCMC, but you were with there basically from the beginning. I remember you coming by right after we submitted and saying, wow, like this really looks good. Thank you for seeing the potential in the ungulates methods. Even when I was a doubter, you believed really from the first time we submitted to NeurIPS. And thank you for mentoring and teaching me so many different things along the way. So to these 4 postdocs and to everyone who's been involved in the ungulate journey, thank you for making it a real success and a real blast. One other collaborator who's not an ungulate, but a good friend calling in from Zoom, Asher Spector. We worked really hard on a project that wasn't related, but you really started showing me the ropes from early in the PhD as how to write research code, how to give good research updates. And it's been a blast playing ping pong with you as well. Yeah, I remember this is a research talk you gave where you used advanced Bayesian statistics to predict that you had a 90% chance of beating me in the department ping pong finals. And yeah, you're super brilliant, so it's not a surprise that the prediction came true. So, but no, thank you for all you taught me, Asher. I really could not have done it without you. In terms of other mentors, I want to say thank you to Libby Taylor and Julie Zhang. These are my mentors in the EDGE program, and you really went above and beyond in talking to me and giving me guidance during the start of the PhD when things were very rocky and uncertain. So thanks for being very patient, giving great advice, and always being there to listen. Of course, outside of class, I have to say a huge thank you to Stanford Club Tennis, to the running club, to the social dance community in particular. We have Toby Bell, the choreographer of the 2024 Viennese Ball, which was truly a highlight of my PhD and made the 4th year so fun. Of course, a big contingent from the Catholic Student Association. Thank you for being such wonderful companions in our journey towards Christ. Here's a nice photo from our All Hallows Eve celebration. Speaking of the church, I have to say a huge thank you to my spiritual director, Father Bob. Thank you for meeting with me regularly and for showing me the light of Christ in my own life and those around me. Thank you for all the blessings you've given me, Father Bob. Speaking of blessings, my girlfriend Tiffany, I think, is probably on Zoom. She's taking in the bus from South Bend. You've been such a blessing in my life, Tiffany. Thank you for all the joy you brought and the wonderful time we've had together. You've been such a nurturing presence, and I love you deeply. And then finally, of course, a huge thank you to where it all began, my family, my brother Walter, my brother Tonelli, my grandma Marion, my grandpa Harold. They've all passed on, but they always had brought such a love of learning and instilled it in our entire family. Both my grandparents were professors, both my grandfathers were professors, and I think they'd be really proud of me looking out for heaven now. Thank you for bringing that love of learning into my family, my father Javier, my mother Natalia, my sister Natasha. My mother and father have always been so devoted to me and give me whatever it takes to learn whatever I want to learn. Thank you to my sister Natasha for being my best friend in the world and for always being there for me. I could not have done this without all of you. Finally, I want to conclude with this image I love. It represents quasi-deer and small and elk and the big. I love that it has this river of instability that elk surmounts with improved stabilization. But also one of the reasons I love this image is it has these green pastures and has this still water. And it reminds me of my favorite psalm, the Lord is my shepherd. So thank you, God, for all the blessings you've given me during my PhD. And thank all of you here today for being with me here to celebrate. Thanks a ton, everybody. So this is the end. This is the end of the public session. So everyone should leave. We'll have pizza right around the corner at 5:30. So come back then, and now we'll do the private session. So thanks everybody. See you later.